Welcome to Lesson 7b, Reflecting Hazardous Area. We're going to discuss the hazardous area for a reflecting ground instead of an absorbing ground. It's pretty much the same material as the previous lesson, except that we had added this extra term for the reflecting ground. Remember, we added that source. So the algebra is a little bit different, a little bit more complicated, but not much. So this won't be a long video. And then I also want to show you an email from a previous student that shows an application of this material. So here's review the reflecting ground case with that additional term. We added that image source, as you recall. And so how do we predict the hazardous area on the ground downwind of the plume or at any z to make it more general? So we can just leave these z's in here and not set them equal to 0 to be more general. That's what I would recommend that you do in your algebra. So what do we need to do? Well, again, just like last time, we have the unknown is y, and we set Cj equal to the PEL. So we'll set the left-hand side. We know everything else. We know all these constants. So at some x, we want to calculate y. So how do we do that? Well, again, we can do it several ways. We can use software and goal seek, or you can do some fancy stuff with MATLAB or ease or whatever to try to solve this equation as is. Or again, you can solve it analytically, and it looks hard, but it's really not. It takes like a half a page of algebra, and I want you to do that. So remember, use this. That's a key. And what that allows you to do is separate these terms into e to the something times e to the something else. And that'll let you isolate that y. But you got to do that twice, and then you have to collect terms. The goal is to put everything with y on the left and then solve for y. You end up taking the natural log and the square root. And so do this on your own. So I'm going to put a big star here and say do this. Make sure you get the right answer and you get the right equation, because I will not have this equation on the equation sheet. I want you to do this. This is part of educational process here to do the algebra. And so you should get, it'll look just like the previous one except be a little longer because you have that extra term. Y equal plus or minus sigma y times square root of -2 natural log of a whole bunch of terms in here that have all these constants and the z's and the h's, etc. And so that is not very difficult. I want you to do that. And I will do now an example problem. And once again, we've seen this problem several times. I'm going to use exactly the same problem that we did last time at the past several lessons, except now we have a reflecting ground. So the only thing I did, I copied and pasted actually and just changed this instead of absorbing to reflecting. Same numbers. So it's the same stack height. It's the same plume rise delta H. We get the same capital H, which is 100 meters. It's the same U. It's the same m dot JS. It's the same conditions. So we have the same class D. So this is all the same. The only thing that's different is it's reflective. PEL, I even kept that the same as the previous example, and I also kept X the same as the previous example. What we want to do is set Cj equal PEL, and you solve for y. And again, you have to use this equation that you derive here. You can double check yourself with goal seek or something in Excel or one of your software, but I really advise you to do this because you're going to have to make plots then also. So you want to do this several times. So let's plug in everything. You should get y equal plus or minus 413 meters to 3 significant digits at this x of 4.85 kilometers. Make sure you do this, get my numbers with my problem, and then you'll have different numbers but the same equation, so that your quiz should be trivial once you get this all put into your software. A couple comments or notes. First of all, let's compare this to the absorbing case that we did last time. We had 250 meters for the absorbing case. Now we have 413. So my first comment is this is not a factor of 2, even though the reflecting ground has a factor of 2, and we're doing this at ground level. Again, I don't know if I mentioned that, but we are doing this at ground level in this example, z equals 0. So you say, well, everything's just a factor of 2, so the y should be a factor of 2. Well, it's not. This big equation that you generate is not a linear equation, and it doesn't add up that way, even though the ground concentration will be a factor of 2 right at the ground, but the y will not. So it's not that simple. You have to actually do the algebra and do it. My other comment is that you should be able to do this for any z above the ground, not necessarily just at z equals 0. That's an easier case, but when you go through this algebra, just leave your z in there. Let z be given and do the algebra with z. You can always set z equals 0 in your software if I ask for the value of y on the ground. I did this with various x's. This was just for one particular x, and obviously in Excel or other software you can do this for many x's and then draw your plots. And I did both for comparison. I did the absorbing one from last time and the reflecting one from this time, and we see it's kind of an egg within an egg, as you might expect. And for the reflecting ground case, this red one, the half width at the maximum is around 8 kilometers, and that's equal to 500 meters at the max. The actual total width is about 1,000 meters or a kilometer. I did this by hand last time, but I adjusted the size here and the scale. Instead of meters, I changed it to kilometers, and I adjusted the scale to make each one of these grids square. This is to scale. You can see the x is kilometers and 1 kilometer is this distance, and y is kilometers and 1 kilometer is that same distance on this. So this is what it actually looks like if you were in an airplane and you could somehow visualize the hazardous area. So for the reflecting ground case, everything in here is the hazardous area. So if this somehow made the ground turn red everywhere the concentration was above a certain level, like it turned all the grass red instead of green, this is what you would see. You would see that area. So this area is actually quite long. It's approximately 14 kilometers in length. And as I said above, it's approximately 1 kilometer in width horizontally in the y direction. Okay, finally, I have something to motivate you. This is an email that I got from a former student. This was way back in 2015, and I added the coloring for highlighting purposes. But I can tell you that when I got this, I remember that day, it just made my day. And so I thought I'd read you this email. I left off his name and the company. I didn't want to put any of that in there, but this is word for word other than leaving out the names here. So I'll quickly read this to you. My name is such and such. I was in your ME 433 class, began working. So he graduated and got this job. One of my first days on the job, my boss mentioned to the group how we needed to obtain the radius of exposure. So he's calling the radius of exposure. This is really the same thing as the hazardous area. They're assuming it's a circle, I guess, in that case. They just want to have some radius of exposure of an actual chemical H2S from our wells in a blowout. And then he talks about the chemical that's in the majority of oil and gas wells. So he recalled the work we did with plume models in class and quickly told his boss that I would be able to handle the project. Attached, you will find he sent me an Excel spreadsheet. I showed my boss and coworkers, and they were blown away by all the calculations and user-friendly design of the work. But he basically took one of our homework problems and made it a little fancier with some of the plots and gave it to his boss. So he had already done all the work. The knowledge of plotting plumes enabled me to take it to the next level, created an interactive workbook. So he did some front end on that so they can enter some values. So you can read the rest of that. But this part is the most important part. I'm sending this email for 2 reasons. First is to express my satisfaction with your course and your teaching methods. Well, I'm teaching a little differently than then, but I think it's actually better this way.
I like this method of teaching. I can exercise while I watch the videos.
Thank you, Arnold, for that encouragement. By the end of the semester, I believe I had learned more than I had in any other class at Penn State. Wow, that's what made my day. The second is that I hope you might share this with your current class as a testament of how applicable the course is in the real world, especially in the oil and gas industry. Hopefully by seeing this, they will realize how important it is to take your class and even more generally school seriously.
Hey man, I'm gonna take my classes more seriously from now on, dude. Me too. Hasta la vista, baby.
That was a wonderful email, and I would encourage you, not just to me, but any professor, if you use what they taught you in your job or in grad school and it really helps you, something that they taught you, if it's me or someone else, please send an email like this. It will make their day. It really motivates us to teach well, and I hope this kind of an email motivates you to take your courses seriously. You never know what you're going to use. I think a lot of students think they won't use what they learn and just get a degree and then you just throw it all away, but sometimes you actually use what you learn. So have fun with the algebra and the quiz here. We get more and more complicated, but it's getting more and more fun, I think. Thank you for watching this video. Please subscribe to my YouTube channel for more videos.